we spent some time basically motivating the idea that the key objective that we want from the perspective of the study of heat transfer, the key thing that we want to achieve is to be able to create some equation that tells me how these heat fluxes relate to the difference in temperatures between the object at this point and the surrounding environment. All right? And so essentially we want to try to create some equation of the following form. Okay? And this is the part in which most of the time, if this were another course, you'd have your professor appeal to some kind of like physical argument, like fundamental physical principles that say, oh, well, the F should be this or that, and that's how we get the following equation. But I'm not going to do that, because the heat transfer is not that kind of science. What we are going to do is effectively show that we can assume the simplest possible form for this equation that makes sense, and then just work with the consequences of that. Okay, so we're not ever really going to delve into like any fundamental physics of like what is temperature and like what is thermal energy. We're just going to show how we can try to create a simple equation for how to relate Q double prime to delta T, and then off of that, figure out what those consequences are going to be. All right? So, what are some things that we can try to investigate or understand about what this function is even before we start trying to do our little mathematical tricks? Okay? From experiment, and in fact, from the very postulates that we use to describe what we think heat transfer is, right? The idea that temperature differences cause heat to move between objects. The idea is that if we assume that this is how thermal energy moves around, whenever we don't have temperature differences, then we shouldn't observe heat transfer, right? If the temperature of this rock was the same as the temperature of the environment, then there is no thermal energy to move around because the system is in equilibrium. That invisible liquid, right, that we call heat, has equilibrated. And so as a result, if we were to draw this function as a graph, right, and we say that, maybe this is Q double prime, and we say that this is delta T, and we have some function that relates them, whatever this function is, which we may not necessarily know what it is, it has to intersect the y and the x-axis at the same time, right? Whenever delta T is 0, Q double prime has to be 0 too. All right, so we'll just say 0. And again, there's no fundamental physical principle that governs this other than the fact that we created the study of heat transfer under this assumption. Under the assumption that whenever delta T, that heat flux and heat transfer occurs as a result of imbalances in temperature. Okay. So whatever the function is, we know that it has to intersect the y and the x-axis at the same time. But what about the rest, right? Because we don't care about, like, this is the most useless piece of information in the sense that this is telling us something about heat transfer in precisely the circumstance under which it does not occur. But there's a couple of other things that we can observe, and they're just going to make things even more confusing, right? Which is that there's no reason that this function should only be of temperature difference, right? It could depend on the properties of the object or the atmosphere, right? It could depend on, I don't know, it could depend on the Young's modulus of the object. It could depend on the viscosity of the surrounding liquid, all kinds of different things. So the fact that we're plotting this is not necessarily wrong, because we can always just fix these quantities and then observe, what is the Q double prime as a function of delta T. But you can imagine that the properties of the specific setup, the experimental setup that we've created, will affect what the shape of this graph will look like. Okay? So what can we even do here? Well, here's something that we can assume. It's not necessarily the best assumption, but it will nevertheless work, so let's try it out. Let's assume that differences in temperature that we care about, differences in temperature in, any object that we could consider studying here on Earth, that those differences are going to be small. Now, it's a little tricky and definitely misleading to say that temperatures are small, or temperature differences are small, because you have to have some kind of measure of smallness of temperature in order to be able to make that claim. And we don't really have an idea, at least not with the understanding that we've developed so far, right? We don't really know how warm or how cold constitutes a temperature difference being small. Like, is the temperature difference between, I don't know, boiling water and the surrounding air large or small? Is the temperature difference between the sun and the earth small, right? We can make those claims relative to each other. So we can definitely say, oh, the temperature difference between the boiling water and the surrounding air is small relative to the temperature difference between the sun and the earth. But we're not talking about that, right? So we have to create this kind of very not great assumption that we are creating a theory of heat transfer that exclusively operates at a regime of very small delta T's, okay? Very small temperature differences, which means that we are focused right around here. So not exactly, right, at 0, but that we are focused on a region that is sufficiently close to 0 that we can say that temperature differences are small, okay? Whatever that means. So we're just around 0. Why does that help us? Well, imagine that you could zoom in to this little box over here. And imagine that you could see what the shape of that function would look like. So based on the sketch, if you tried to plot it, you'd see something that looks like maybe like this, with like a slight curve, okay? But then what would happen if I zoom in even further, right? If I zoom in even further, what starts to happen is that as long as this line isn't like some kind of weird fractal, this line gets closer and closer to looking like it's straight, okay? Because as I zoom in, all of that information about the curvature goes away. You can try this out yourself. Draw a line, look at it, you know, magnify it under your phone or with a magnifying glass or whatever, and you'll see that eventually, assuming that you can't draw fractals, that this thing will wind up looking like a straight line. And so what we're doing when we assume that heat transfer operates, that the theory of heat transfer operates at small delta T's, is we're basically going to say we are operating at delta T's that are so small that we can assume that this line looks straight for any delta T's that we care about, right? That all the delta T's that we care about are inside this little range of the box such that this looks like a straight line. And what that winds up meaning, okay, is that from the perspective of the construction of this equation, we no longer have to worry about what the whole function looks like. We only have to care about what the function looks like in a neighborhood that's very close to delta T being equal to 0, okay? If that function looks like a straight line, that means that there is a linear relationship close to delta T equals 0 between Q double prime and delta T. And so what that winds up meaning is that we can generate a linear relationship, an approximation of a linear relationship between Q double prime and delta T, which is mediated by the slope of that line, which we would have to empirically measure, right? And the slope of that line would be described by this constant h. And this h is usually referred to as a heat transfer coefficient. Sometimes you'll see people give h different names. They'll call it a convection coefficient or they'll call it a film coefficient. And really those are just descriptive terms associated with when we use this model, right? When we use this particular equation, which is most of the time in convection. And we'll get to that in a second. But the point is that all of the physics, all of the data that has to do with, you know, the physical principles of how does this object actually transfer heat, what is the relationship between Q double prime and delta T, all of that information gets dumped into this coefficient h the instant that we make this approximation, this linearization, well, where we say, okay, well, we only care about q double primes in neighborhoods of very small delta t's, such that this function is well approximated by this. But the trick about this is that, okay, it looks like we've pulled quite a rabbit out of a hat, in the sense that we took this arbitrary function, we just created this. But this h can depend on anything, right? This h can be a function of this or anything else in the system, right? And so what we've essentially done is that we've created this equation and then dumped all of the hard stuff into the h. And then the h we would have to find by running detailed experiments where we study what this heat flux is as a function of temperature differences between an object in the atmosphere for different material properties. So if I take this rock and I switch it out with another rock of the same shape but a different material, that h is going to be different. If the wind is blowing over the rock in a different way from one day to the other, the h is going to change too. Right? H depends fundamentally on the physical setup that's associated with these two things, the object and the environment. And so unless we actually start to dig into empirical data, we are not going to have a mechanism for us to be able to understand what h is in systems. We have to construct experiments or have people do experiments for us that tells us what the h is between two different types of objects, and then use that to be able to create estimates for what q double prime will be for a given delta t. Like I said, very ad hoc, right? No physics, no physical arguments involved. And the reason, just to finish this off, the reason that usually heat transfer coefficients are often referred to as convection coefficients is because we use this equation almost always to model that process that we had referred to as convection before. And what was that process? Just as a reminder, we had said that convection was whenever you had heat transfer that was occurring between a solid object, or actually between two objects where one of those objects was a liquid or a fluid. Okay? So maybe you have two liquids that are mixed together. Maybe you have gas that's flowing over a solid. So like here, right? So this is a situation where you have a solid and then you have air, a gas surrounding it. And so these sorts of scenarios where you have at least one fluid involved, we would call those scenarios convection. And that's why this h is called usually a convection coefficient, because it is related to how we model these systems, okay, which is with this equation. This equation winds up being very easy to use because we can say relatively straightforwardly, oh, well, the temperature of this piece of the surface of this object is something. And the temperature of this piece of the surface of the object is something, right? So we can define the temperature at the surface of the object pretty easily, right? And then we can also define some arbitrary uniform temperature for the environment, right? So we can say that the air is at, 23 degrees Celsius, and then we make this very ad hoc, again, technically incorrect assumption that the air surrounding this object is just at this uniform temperature of 23 degrees Celsius. And in that scenario, so for example, let's suppose that I was considering the temperature of this front surface, then it's very easy for me to just say that maybe delta T is just the temperature of that surface minus the temperature of the environment, which I'll call T infinity. And then we define this as being my delta T. I find via experimental data what the h between these two objects are. And then I use that connection to find my q double prime. And if I wanted to try to figure out what the net heat transfer rate was, if I wanted to add up all of these heat fluxes and get a net heat transfer rate, well, I would just calculate the heat flux on every piece of this boundary and then integrate it over the surface to eventually obtain the net heat transfer rate. One of the things that makes this equation easy is that it is very obvious where heat goes, okay? We've already come up with the idea that thermal energy flows between objects that are not in thermal equilibrium and that whenever an object has a large amount of thermal energy, it means it has a large temperature, right? So increases in temperature correlate to increases in thermal energy and vice versa. And what that means is that if the temperature of the object is larger than the temperature of the environment, then that means that we have an unambiguous way of defining where those heat fluxes are going. They're going outside. We just take a look at the surface of the object and we say, okay, which direction is outside? And then we just draw a little arrow and we say, well, that's the direction in which the heat is being transferred in, right? We can do this for every piece of the surface. And in this particular case, it's very easy to do, again, because all we have to do is investigate, is this temperature, is this difference in temperatures positive or negative? And then based off of that, are the heat fluxes going inside or outside? And this boundary that we've created between the object and the environment makes it easy for us to figure out what the inside direction and the outside direction are. Right? So we don't have to rely on any vectors or vector mathematics for now. All right? And so now that we've done this, the next step is to basically take this equation that we've created and then try to do some concrete exercises, or at least an exercise or two, to understand how we can apply this equation to an actual real physical setup. So that is what we are going to do next.